Hello everyone, thank you for attending the BAS Electrochemical webinar 2023 June. I'm Minho from International Sales Team and I will be the moderator. Today, it will be the sixth lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and applications, with a focus on organic complexes. Introduced by Professor Masa-aki Haga from Chuo University. Today's theme is Coordination Chemistry and Electrochemistry, Tips in Electrochemical Measurements.
Hello. In this series of seminars, so far, I have been talking about the various electrochemical techniques such as cyclophotometry, rotating disk electrode, and spectroelectrochemistry. I also touch on the electro reaction mechanism. If you have any questions, please write me directly. Today, I'd like to talk about tip and detail for electrochemical measurements. When performing electrochemical measurement in 3 electrode cells, as shown in figure, there are several notes to be considered. Today, I will discuss some of them. First, what kind of solvent and supporting electrolyte were used? Depending on the solubility of the analyte, we should select suitable solvent, either aqueous or nonaqueous solvent. Once you select the solvent, next, supporting electrolyte. In aqueous solution pH becomes also important. By choosing these conditions carefully, we can get the nice result to access the successful electron transfer chain sometimes. Recently, new solvent systems such as supercritical fluid and ionic liquid have been introduced in the electrochemical field. The challenge for use of such new solvent systems play an important role in opening up new chemistry. At the end, the selection of reference electrode is an important issue, so I touch on the reference electrode. We also consider the IR drop during the electrochemical measurements. Let's consider aqueous solutions. Here shows potential windows and Prof diagram in water. Chemical term potential window is the available range of potential in which the solvent and the supporting electrolyte do not react and no electron transfer between the working electrode. In aqueous solution, the solution pH determines the potential window range. In aqueous solution, the water reduction and oxidation occurred at both negative and positive potentials, which determines extent of the potential windows. And these redox potential varied with solution pH, as shown in this Prof diagram. Furthermore, electrode material affected redox reactions because of the overpotentials for hydrogen reductions and water oxidations. Here shows the order of hydrogen and oxygen overpotential by electrode materials. For the negative potential side, glassy carbon and mercury have a large over potential windows because of their slow kinetics for hydrogen reductions. Therefore, carbon electrode is often used. Mercury electrode is a good electrode for the reduction in aqueous solvent. The important quality for the solvent is the ability for supporting current flow in solution. Therefore, the ion conductivity is the key parameter for electrochemical measurements. When using organic solvent, it is important to consider the polarity of the solvent, the temperature range of the liquid, the redox range, and the acidity and basicity of the solvent, and the solubility of the analyte and supporting electrolyte. In organic solvent, high ionic conductivity after dissolving the analyte and supporting electrolyte is important. Here shows the table for the ionic conductivity in different solvent systems. In water, conductivity is 0.8 to 0.3 Siemens per centimeters. In hydrochloric acid, however, in acetonitrile with tetrabutyl ammonium hexafluorophosphate case, the conductivity is about 10 times smaller than that in water. In low dielectric constant solvents, such as dichromethane or tetrahydrofuran, low conductivities. In these solvents with low dielectric constant, the high solution resistance and large ohmic loss occurred. Commonly used in acetonitrile tetrabutyl ammonium hexafluoride in solution electrolyte systems, potential window from +3 volt to -3 volt is available. A redox flow battery using the aqueous vanadium ion solution is known as a system for storing electricity generated by solar power. This is a system in which the redox pairs with different potentials are stored at the anode and cathode, and current is extracted by bringing the two solutions into contact when necessary. Currently, an aqueous and the voltage contained about 1.2 volt. Since a larger voltage can be extracted by changing water to a non-aqueous solvent, several studies have been conducted on the use of non-aqueous solvent. Here the ionic conductivity of the solvent and supporting electrolyte combinations are listed. As expected, acetonitrile and 1-butyl-3-methylimidazolinium in the supporting electrolyte bis 3-fluoromethyl methanesulfonylamide is a good choice. The severe tris-acetylacetanoate vanadium is shown here. The vanadium 2,3 couple is -1.6 volt. The vanadium 3,4 couple is 0.4 volt, and voltage about 2 volt can be obtained. In a system using the ionic liquid as solvent, 2.4 volt can be taken out. Therefore, by changing the solvent from water to non-aqueous solvent, it is possible to increase the extraction potentials. For the redox reaction of the analyte in solvent electrolyte solution, not only Faraday current, but the redox reaction of analyte, but also the double-layer charging current flow. For the Faraday current, the solvent and the supporting electrolyte also undergoes an electron transfer reaction with the electrode at the higher or lower potential range. This is the factor that determines the background potential windows. For charging current, once the potential step is applied, the current is decayed in exponential manner. On the other hand, the Faraday peak current is proportional to the square root of the sweep rate. In CV measurement, as the scan rate is increased, the charging current proportional to the first order of the sweep rate, while the Faraday current varied with the square root of the scan rate. Hence, the CV peak at higher scan rate is shown here, but the peak becoming buried in the background of the charging current. Electrode size and cell time also play an important role for the transient electrochemical measurements. The current decay by the potential step is given by these equations, in which solution resistance and double-layer capacitance are involved in the cell time constant. The electrode size plays an important role for the shorter temporal domain measurements. Here the table for the size dependent on the resistance, double-layer capacitance CDL, and cell time constant are given in these equations. In microdisc electrode, the diameter becomes smaller, the resistance becomes larger. Double-layer capacitance increase with the square. Therefore, the cell time constant strongly depends on the electrode size. For example, in the case of interfacial capacitance per area, CDO is 20 microfarad per centimeters. Conductivity is 0.013 Siemens per centimeters. 1 mm diameter cell time constant is 30 microseconds. When electrode size becomes smaller to 5 micrometers, 170 microseconds. So, if you will measure the faster time domain, you should use the smaller ultramicro electrode. Let's continue talking about electrode. When the current potential curve is measured with the electrode, two different current responses are observed as the extreme case, depending on the electrode. One is that no charge transfer across the electrode solution interface occurred. Therefore, little current flow under the applied potentials. This type of electrode is called an ideal polarizable electrode. The example is mercury electrode in potassium chloride aqueous solutions. Another electrode is that the potential does not change under the current flow. The typical current response shows a vertical line at one potential. The potential does not change while the current flows. This is called as an ideal non-polarizable electrode. AZCL electrode or SCE electrode is this type of electrode. The potential does not move upon the passage of current. Therefore, this type of electrode is used as a reference electrode. Here is a general requirement for the ideal electrode from the viewpoint of materials and electrochemical properties. First, high electroconductivities, and second, hard and durable. The third, homogeneous microstructures through the bulk. 4. Reproducible physical, chemical, and electronic properties. 5th, good chemical inertness. 6th, low and stable background current. 7. Morphological and microstructure stability over a wide potential range. 8th, rapid electron transfer kinetics for a wide range of Redox systems. 9th, easily fabricate, shaped, and inexpensive in cost. Commonly used electrodes meet these requirements. Carbon electrodes are the most commonly used electrode in electroanalytical chemistry. In particular, their application to biological samples has been popular. As carbon electrode in the laboratory, a highly oriented pyrotic graphite electrode that provides an atomically flat surface is used. The electrode is composed of two-dimensional sp2 carbon graphene plane, which are oriented in a superposed manner, resulting in a significant difference in conductivity between the in-plane and perpendicular directions. Glassy carbon is also called vitreous carbon. It is amorphous material with intermoving structures of graphite ribbons obtained by sintering polyacrylonitrile or phenol resin at high temperature under inert gas. The background current on Cb is strongly dependent on the pretreatment of carbon. Here show the example taken from the reference. In figure 1 is HOPG background. Little charging current and wide potential window is available. Polished glassy carbon shows large background charging current than that for HOPG, but relatively wide potential windows. However, once the glassy carbon electrode is scanned to positive potential directions for several times, several new peaks appeared, indicating surface carbon sometimes somehow oxidized. Other carbon electrode, carbon fiber, recently carbon nanotubes are reported for the electrochemical applications. Further, boron-doped diamond is a new phase for electrode materials. For the carbon electrode, you can find extensive report in ALS website. Boron-doped diamond electrode, abbreviated BDD here, has attracted much attention as a new electrode material, in particular for the biological sensor applications. BDD consists of a diamond in which approximately one atom in 1,000 has been replaced by boron, giving the material p-type semiconductive properties and yielding the hardest conductive carbon materials. BDD electrode exhibit a wide potential window with low background current, and also significant chemically inert, same as platinum electrode. Recently, diamond electrodes have become commercially available, even from chemical suppliers such as Sigma Aldrich. Even expensive though. Here is the background current on CV in different solvent supporting electrolyte conditions. The potential window is reaching 5 to 6 volt range. Even in water, the potential window of 5.19 volt was achieved on low boron doped diamond electrode, which is amazing. In order to obtain wide potential window when using non-aqueous solvent, careful purification and dehydration of the solvent supporting electrolyte system is required. Each researchers design their own system with care. It has been reported here. One of the example, the electric cell can be connected to a vacuum line to measure up to -3 volt on the negative side and measure up to 3.5 volt versus AgCl on the positive side. The redox reaction of conjugated pi-electron molecules using CV provide important information of molecular energy level as a fundamental data from the viewpoint of molecular design. In order to get the information of homo-lumo level, it is important to know how many multi-step electron transfer chains can be observed. I have shown two examples here. The first one is C60 fluorine in acetonitrile-toluene mixtures at -10 degrees. You can see the successive 6-step reduction waves. The second example is tris-4,4-bis ethoxycarbonyl 2,2-dipyridine ruthenium complex. In this complex, the 3 dipyridines are first reduced one by one to become 3 monoanion radicals, followed by another 3 reduction of peripheral ligand to 3 dianion radicals. Here is another example for many successive reversible peaks observed in trinuclear ruthenium complex linked by pyrazines, cluster of cluster complex. And in the slide, left-hand side is 3 trinuclear cluster unit linked by pyrazines involved 9 ruthenium ions. Right-hand side is 4 trinuclear ruthenium unit linked by pyrazines, which is contain 12 ruthenium ions. Left-hand side, CV peak is counted 11 peaks, and right-hand side, 14 reversible peaks observed. This is the most beautiful CV I have seen before. I would like to change the subject and introduce you to a new solvent systems. One of the new solvent is the supercritical fluid. There are 3 states of the matters: solid, liquid, and gas, and the interchange between these phases depending on the temperature and pressures. Here shows the phase diagram water, which shows only liquid phase and water vapor state. As both temperature and pressure increase, it reaches as a critical point. About the point, it becomes impossible to clearly distinguish between the liquid and gaseous state. Phase boundaries vanished. A substance in this state is called a supercritical fluid. The critical point is defined by critical temperatures and critical pressures. Ammonia, water, carbon dioxide, and acetonitrile are well-known examples for the supercritical fluid. For electrochemical measurement in the supercritical fluid, the electrochemical cell, which withstand high pressure and high temperature, is required. Here is an example made of stainless steel vessel. Supercritical fluid as a solvent used for electrochemical measurements are listed here, and also their critical temperature and pressure along with their critical density and dielectric constant are tabulated here. Supercritical carbon dioxide, which is commonly used, have a low dielectric constant and a large IR drop on potential application. Therefore, it has been reported that adding water or acetonitrile to the supercritical carbon dioxide, which make it a suspension, improves the potential response. Also, the supporting electrodes is important to achieve high solution conductivity and reduce IR drop. The combination of fluorinated aryl borate anion and tetraammonium cation, as shown the CPK model here, is often used as a supporting electrolyte in this critical fluid systems. In the case of supercritical carbon dioxide, acetonitrile or methanol was added to dissolving supporting electrolyte. However, it is necessary to confirm that system is a single phase because it may become 2 or 3 phase separation. I'd like to present some example of application of supercritical fluid in electrochemistry. First, this figure shows an example of CV measurement of decamethylferrocene using supercritical fluid as a solvent. The temperature is 309 Kelvin and the pressure is 17 megapascal. The working electrode is a gold electrode with a diameter of 0.5 millimeters. Reversible wave with large peak spacing are observed. The large peak spacing is due to the IR drop, which is attributed to the low conductivity of the supercritical fluid due to its low dielectric constant. The diffusion constant of the material is 5 multiplied 10 to the minus 5 square centimeters per second, which is not much different from in ordinary solution system. Another example is electroplating. The advantage of using supercritical fluid for electroplating is that it's almost no surface tension of supercritical fluid. So the surface can be plated uniformly and smoothly, and the penetration into the pore is good. When copper acetonitrile complex are dissolving in supercritical fluid, an electroplate on silicon nanopores arranged in the hexagonal crystal systems. Copper nanorods are formed in the nanopores. Thus, supercritical fluid is a very useful medium for nanoscience processing. Ionic liquid, formerly known as the molten salt, are salt composed of cations and anions that are in a liquid state at relatively low temperatures. Recently, ionic liquid has been used in many fields, such as solvent for dissolving cellulose, semiconductor membrane in electroplating, and electrolyte solution in energy storage batteries. Here are the chemical structures of cations and anions used in ionic liquid. Cations include pyridinium and imidazolinium, quaternized ammonium, pyridinium, and phosphonate, etc. And as an ion, trifluorate, bis-trifluoromethane sulforamide, sulfonate, chloride, bromide, nitrate, tetrachloroaluminate, perchlorate, etc. The combination of cation and anions gives a fluid with ion conductivities comparable to many organic electrolyte solutions. These ionic liquids are thermally stable and low vapor pressures, so it is very useful. Some of the ionic liquid is a little bit viscous, but they have a wide potential window in the range of 4 to 6 volt range. Of course, it also depends on the impurities such as water and excess halide ions, so we should be careful for the purification. As an electrolytic solution similar to ionic liquid, water-based lithium-ion batteries using hydrate melt have attracted attention because of their high energy density and high voltage, even in water systems. Here, what is used is the molten hydrate made by mixing lithium bis-trifluoromethane sulforamide, lithium bis-trifluoroethane sulforamide, and water in precise molar ratios. Once mixtures, they can become transparent liquid. When lithium NTF is simply dissolving water, hydrogen evolution is observed with lithium titanium oxide in CV shown in figure A. Also, integration of lithium ion is not observed in lithium mangan nickel-mangan layered solid. On the other hand, in the case of molten hydrate, peak associated of reversible integration are observed at the anode and cathode side, and potential range is also as high as 3.1 volt. DFT-MD calculation for salt in water and water in salt indicate clear difference. In water in solid case, all the water around lithium ion is coordinated lithium, and the absence of free water is thought to be the reason for the availability of such high potentials. In other words, molten hydrate can produce battery with high energy density. Interesting new research area for aqueous system in electrochemical measurements. When a current flows through the measurement cell in a 3-electrode system, a voltage drop proportional to the product of the resistance of the solution and the current flowing through it occurred as shown here. This is called IR drop. In CV measurement, the IR drop appeared as a shift in the CV peak. The larger the IR drop, the larger the peaks interval between the oxidation and redox peaks. The equivalent circuit of 3-electrode cell connected to the potentiostat can be written here. Here, on each electrode, the resistance and capacitors are present, especially between the working and reference electrode, remain as uncompensated resistance, which causes IR drop. The logging capillary was devised to reduce this solution resistance. These days, in a control device, including potentiostat, the operational amplifier is equipped, so the application of positive feedback can compensate the IR drop. The shape of the logging capillary and distance from the electrode greatly affect the IR drop. For this reason, it is recommended to set the logging capillary 2D apart from the outer diameter D of the logging capillary. Not only the diameter of the capillary, but also depending on the electrode geometry, planar electrode is the most simple treatment. Finally, reference electrode. The reference electrode is an electrode that maintains a constant potential independent of the current flowing in the system, in the 3-electrode system. The potential of the working electrode is controlled as the potential between reference electrode and working electrode. The non-polarizable electrode mentioned earlier is used as the reference electrode. As a reference electrode actually used for aqueous system, mercury chloride with saturated potassium chloride is commonly used. We call it SCE as a short. Silver chloride gives the stable potentials in chloride solution. As a protic solvent, as shown in this table, AgCl or Ag plus can be used with a variety of organic solvent. Ferrocene-ferrocenium couple is also used for many organic solvent and used as a standard couple. It is a good idea to measure and report the potential of ferrocenium ion as a standard couple, since it acts as a marker for other workers to compare the potential in the same solvent. An ideal non-polarizable electrode is needed as a reference electrode, and the potential of standard hydrogen electrode is set to 0 volt. The potential of saturated caramel electrode in aqueous solution is minus 0.244 volt, and AgCl is minus 0.199 volt. The conversion equation between the two is as shown here. Note the hydrogen electrode potential is 0 volt when the solution pH is 0, but potential also shifted when the pH of the solution changed. In the case of non-aqueous solvent, Ag plus in acenyl is often used, but ferrocene is used as an internal standard and measured together with Ag as a reference electrode. Here's one example in cyclic diagram. When the different reference electrodes were used, but the ferrocene-ferrocenium pair was measured and converted versus to ferrocene-ferrocenium coupled. And you can see the same complex possess the same potential versus ferrocene-ferrocenium standard. Therefore, the researcher recently used ferrocene-ferrocenium couple as the internal standard. Finally, I'd like to once again review the protocol for measuring CV in non-aqueous solution. First, we determine the potential window by measuring the background only in solvent and supporting electrolyte. Check the electrode and solvent system are clean. After being measured the background, the analyte is added to the solution, and after the dissolution of analyte, the CV measured step. At the beginning, the open circuit potential, where the zero current between the working electrode and counter electrode should be measured, and then the CV curve is recorded for both positive and negative potential directions. And also, changing the applied potential range and changing the scan rate is also important. Finally, by adding ferrocene as an internal standard, we can measure the CV, and then all peak potential were converted to the value versus ferrocene-ferrocenium as a standard. These are the basic operation of electrochemical measurements. As we discussed today, there is a possibility we can see new aspect of the same compound by changing the solvent and electrode measurement conditions. Although electrochemical measurements require careful attention to detail, we hope that repeated measurements will make your electrochemical measurement one of your analytical tools in your research. Today, I talked many tips and details for electrochemical measurements. First, selection of solvent, supporting electrolyte, and electromaterials are important, and you should try to measure it with different electrode or supporting electrolyte systems. When looking at the electronic state in the molecules, by observing many electron transfer chain provide a basis of cutting-edge knowledge for the materials, not only organic solvent, but also ionic liquid and molten hydrate water, such as water in salt provide a complete different potential windows and open up new chemistry. The reference electrode must be a non-polarizable electrode, and it is important to select a reference electrode suitable for both aqueous and non-aqueous systems. Here is a reference which I told today, so please read carefully in these references. And if you have any questions, please write me directly. Thank you.
Thank you, Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news. Also, you can watch the Professor Haga's past 5 lectures. The next webinar is already scheduled for August 2nd. For today, thank you and have a nice week.